Good afternoon. So, slide is visible.
Yes, sir.
So, okay. First, before we start today, today is the I think last class before medicine. So, I think if you have any doubt regarding what we have discussed in this mid semester, before mid semester, then you can ask. Okay. Otherwise, what I'm thinking, we continue this thing, and we'll see how much we can complete. Maybe neural net is not fully completed, but anyway, that up to which we'll today will cover. That will be the syllabus of the mid semester exam. Okay. So if you have any doubt or anything or any queries regarding this thing, as of you, most of you know that way. So we will do the similar thing. Our, if I'm not wrong, our mid-semester exam is 3rd March, 2 to 4. You check with the academic section examination timetable, and and other things is it is a 2 hours exam. Maybe marks is maybe 40 or 50, something like that. Okay, so if you don't have any questions, let us continue that how much we can complete into today's class. Okay. So what we were discussing in the last class, that basically we discussed about that the limitation of the singular perceptron, and those problems or those data distributions are linearly separable. A singular perceptron can be used as a classifier. So decision boundary for singular perceptron is essentially a kind of linear or straight line, two-dimensional case. Okay? Okay, so now we see that if there is a the data distribution is such that it is not linearly separable, then we have to have at least one hidden layer. So this is the concept of multi-layer perceptron. So we see multi-layer perceptron later stage. So slowly we know that what is the learning algorithm. So when we are training a network, we not only present it with the input, but also with the value that we have required the network to produce. That means, as you know, it's a supervised setting. And in this supervised setting, just a second. Okay, so this is a supervised setting, and this supervised setting is basically given by this. The training data set is in form that we all know. Then this X is basically this X is basically x1, x2, xn. So it's an n-dimensional feature. Okay, and this Y is the class belongingness. So into this is the Y class. So Y may be binary or multiple class. So this is the thing. Okay. So what we have to do that we have a W vector. So this W vector is basically a set of weights for different neurons. And we have to learn this W vector such that uh, we can, given this X, we can get the corresponding Y, where XY is the training data. Training data sample, or training data. Okay. So this sorry, actually you was there is a network was disconnected. Okay, the slide is visible.
Yes, sir.
Okay, fine. So as you know that these are the a few things that we have already discussed. That is our inputs. Okay, this is some bias term, and this is our some sort of non-linearity over there, and okay, and there is some weight, WPS, something like that. Okay, so this is the non-linearity, and this is the output. So another thing is important, that is when we are the learning rate, as we have seen that in the case of how the weights are being updated, this learning rate is going to control the you can say that rate of convergence, or how quickly it tries to learn. Okay? Rate of convergence of the algorithm. So it also dictates that how quickly the network converges. So it is said in method of experiment is simply typically 0.1 or 0.01, something like that. Some this kind of very low value, something like that. So these are the very simplistic setting of the learning algorithm. Now another thing that we know, with the conceptually we know this, that if there is some sort of data points like this, so this is called decision boundary. Okay, in simple cases, divide feature space by drawing a hyperplane across it. Since in a 2D case, it is a simple. If it is a d-dimensional case, then d minus one dimensional hyperplane. So this is known as decision boundary. So discriminant function returns the different values on the opposite side. So that is the, if it is a discriminant, if it is a hypothesis function, h of theta, then in either side of this, it will go either this will be positive or negative. So this is the thing. which can be classified in linearly separable. So that this is basically considered the linear separability problem. Some data set are linearly separable, some are not. We will see later. So linear separability case, it has been discussed in this format. It is linearly separable, this particular thing, and sometimes it is this. So this is the example of linear separability. Okay. Now, here you can say that this is a kind of linear separable problem. So it's a plus signs is either side of and minus signs into different side of this decision boundary. Okay. And here you can see that there is no single line can separate this point. So it's a kind of Zor kind of problem. So at least two lines is required. One is, sorry, maybe this is the one. This is another. So that is that is two separability. So perceptron is able to represent some useful function and xy choose weight this one w1 w2, but function that are not linearly separable or are not representable. That we have also seen in the course. Okay. So here you can say the capacity of the single neuron. You can see that this is the odd problem, the AND problem, and this is AND in a different way actually, x bar x2 and x bar. So now you can see that this Zod problem can't solve nonlinear and separable problem. So you can do one thing that you can one important aspect is that you can transform data points. You can see that here these data points are these two data points. Here exactly the this is x1 axis, this is x2 axis. Now to change this coordinate system. Now that is one of the solution. So the coordinate system is now it is x1 bar and x2. This is the coordinate. Now initially it is x1. Now it is x1 bar x2. And it is now initial x2. Now it is x1 and x2 bar. Okay. So we change the coordinate system. And if you change the coordinate system, then these points are projected. These are different space. It's the dimensionality is same, but even the axis are changed. So is a different. So this is the called transformation. Kind of this is a non-linear kind of transformation that the axis is changed so that these two data points are projected or mapped here, where these two data points are in a similar position. Now, due to this transformation, this particular problem is now linearly separable. You understand that this is one problem that we have seen in the case of what support vector machine. We have a vector machine, you use a kernel trick kind of thing so that we can project the data points in a other dimension. Here the dimension is not that, but in other coordinate system of the similar dimension. Both are not that, is not that much different. Okay? So this is one of the kind of solution of this particular problem. Okay. If you have any questions. because this is very interesting. Okay, now that you can, but how these are actually changed, that is being mapped in this way. Okay. So now another question is that hyperplane partition. So an extra layer models a convex hull. Now an area with no dents in it, perceptron models but can't learn sigmoid function learning of convex hulls, two layers at convex hulls together, so sufficient to classify. So the idea is the thing are the idea is basically this. Another potential problem of non-linear separability is what we said, that in the case of this input layer, we put a hidden layer, and this is the output. Now we say that a single hidden layer is good enough to solve most of this problem. Even you would be surprised to know that the theoretically any classification problem can be solved in a kind of neural net with a single hidden layer. But it is extremely time consuming. We don't know when it will converge. Okay. So what we generally do, that in theory the further layers basically not doing much help, but in practice extra layers may be better. That we'll see when we discuss about what is the motivation of deep learning. That particular things we will discuss. Now, this is basically the idea that depending on the number of layers, how the problems are being taken. Just for example, single layer thing, this exclusive OR cannot be solved. You can see here. Okay. So classes with meshed region, this is the way. I think it's the most general region shapes is something like that. So half plane bounded by hyperplane. So if you have a two layers, there's a one hidden layer, convex open or closed regions. So you can solve this problem in this way. So this exclusive OR problem is with another hidden layer. And this look like something like this. Three layer, this is the much more categorized in this way. Arbitrarily complex, limited number of nodes. So this particular thing is abstract even with two layers. And you understand in our deep thing, how many layers is it? It's maybe 50 layers, 100 layers, more than 100 layers. So it is a very, very complex decision boundary or decision surface to visualize. So, but we generally do that. Now, here you can understand that what is the single layer perceptron. This is the concept of the single layer. This is the input and this is the output. So that's very simple of single layer perceptron is what we have said, that we have a single layer and this is the inputs are coming. With some grades. Something same similar. So it's the one output, and here it is a 2, 3 output, something like that. Now this is a summation, and we put some sort of nonlinearity here, there. So this is the simplest form of this. Now is multi-layer perceptron, at least one hidden layer. So this is the one hidden layer, and this is the corresponding different weights and the links in that. Okay. So multi-layer perceptron may be with two hidden layers. This is more complex kind of structure, but it is just kind of this multi-layer perceptron. Okay. So this particular thing just full as a pictorial diagrams of this. Now we slowly try to understand that more complex neural networks. Singular nets have limited representation power. So you can say the representation power is limited for singular perceptron as you understand it. This can only solve the linear separability problem. Multi-layer perceptron or neural net with nonlinear hidden unit may overcome the linear separability problem. With nonlinear hidden unit may overcome the linear instability. Every Boolean function can be realized by a network with single hidden layer. So all the Boolean functions that can be realized with single. Every bounded continuous function can be approximated with arbitrarily small error by a network with wide hidden layer. But these results are very much theoretical. Okay, but that thing, randomly bounded continuous function can be realized, but how much time it will take to convert to any function can be approximated to arbitrary accuracy by a neural network having two hidden. So if you have a two hidden layer, any problem can be solved, but it is not practically that much useful. And that's why this will be helpful multiple layers. We'll see later. So here we can say a typical diagram of a neural net with two hidden layers. Okay, that you see first layer this your layer. Now this network, particularly this network, is called feed forward network. Because you can see the inputs is basically the training or inputs this is the input flow and this is in this direction, in forward direction. But one thing is important to understand that the error is basically find here because you see that there is a two thing. Y is the uh, targeted output. That is supposed to be. And Y hat may be the predicted output. What actually we get. So there is a difference. Some kind of thing, this kind of difference. And this is kind of error. And as you see that if you have to take error gradient, then that we have to calculate this. Okay, error, this is the gradient of error with respect to the Wi's. Where it is the Wi's, these are the Wij for the ith neuron, input neuron to jth output. Okay, so this is the way. So these error signals are coming in this way. Okay, so we can say the error gradient back propagate. Okay, that's why when see later a particular algorithm, what will this training algorithm, they will say the back propagation. Okay, this is the term or main name coming from this error gradient. The error gradient is back propagated. Okay, so this is the one of the major aspect of neurones. Okay. Now we want to understand what is the uh, standard or practical model for a multi-layer perceptron. Okay. So in this multi-layer perceptron, that is a single hidden layer. So it's a bit simple. So it is a single hidden layer. Okay. Hidden layer activation is basically this. V1. So AX is what? That is W1 1 of X plus bias. So activation is basically this A are actually this. So if you try to find out what is A, that is, I can say A is bit written in this way. I is equal to 1 to, let's say K input neuron or N input neuron. WI XI. These are the A plus B. And what is the hidden layer? We can put that HX, that is the hidden, we can put a G over A. Or you can say AX or A, whatever, same thing, A. So this G is a non-linearity. Sometimes it can be written G of Z, if you are sigmoidal, 1 by 1 plus to the power minus Z. Okay, so this G is defined in this way. Okay, you can say the hidden layer is basically this. This hidden layer is there is a non-linearity over that, and this connection will give you this particular thing. Okay, and we put a non-linearity to that to get this hidden layer. So this is output layer is obviously what? Output layer is this. Fx is equal to output of, you say B2 is another B2 is basically coming in this layer. It is a base of is B1 over this input layer. This is B2 or the hidden layer. B2 plus W2 transpose H1x. This H1x is this. H1x. So this is your output. So this basically the same thing. We are basically doing the same thing over here. This is the first layer, this is the second layer. Now, what is softmax? So for multi-class classification, we need a multiple output per one output per class. So if there is a multiple class, okay, let's say K class, a K output class. So here input neuron, so you have to, there is something like that. Now every neuron, output neuron will give you some value. Some value. Okay. What is this value? That expectation And that is very interesting, that expectation of A1. So this is the A1, this is A1, this is A2 or something like that. A1 by expectation of all this and summation of this. Okay. So here you can say, just for example, if there is a, I can show an example that there is a, let's say there is an input-output connection. I'm not writing in this kind of, all these things I'm not writing. There is some connections. And there is a input is being given to an image, that is cat, okay? And these outputs are basically giving, one is cat, one is dog, one is horse. This is the thing. So you can say that the softmax value is 0.7 and 0.2, 0.1. Okay. Since it is a highest, so it is okay. So it is a cat because it's a cat. So this is the wing. So the output class should be a cat. But so the similar thing here. The output is basically giving a probability, and which is the most probable class. So the probability is highest that we can belong. So strictly positive, sums to 1. You see, sum is 1 because 0.7 plus 0.2 plus 0.1. So this is predicted class is the one with highest estimated probability. So this is 0.7 highest estimated probability. So this is called the, so some sort of the expectation of what is the probability of E1 by all the expectation. So that is the, okay. So this is the way we generate the softmax. Okay. Now here also another thing, that this multi-layer could be L hidden layers. So a number of hidden layers is high. So layer pre-activation for k is equal to 0. So this is something. If we say what is the in a particular hidden layer, let's say it's a kth hidden layer. So k of x, okay. So bk is your bias term of this particular. Then w is a vector k h of k minus 1, because from the h is coming from the previous layer, k minus 1 into x. Okay, so hx is basically that it is coming the previous layer, so it is coming from the previous layer. Hidden layer activation k112 is basically, so this hk, now this is hk minus 1, this is kind of ak. So hk, this is the previous layer, now it is hk. How is going to this hk of x equal to g of ak of x. So this is ak of x. Okay, so this is the output layer is obviously this is a of l plus x. So this is the output l number of hidden layers. So it is l plus 1. Okay. So this is the way the multi-layer perceptron is. And this is feed forward. So in this way, the input, this is the output. This way. So if you have any question, you can ask up to this. Okay, so what are the different types of layer? Is input layer, introduce input values into the network, no activation function or other processing. Hidden layer perform classification of features. Two hidden layers are sufficient to solve any problem. Features imply more layers may be better. Output layer functionality just like hidden layers. Outputs are passed on the world outside the neural network. So these are the three different layers. These are the very this thing. Now, how this MLP will help to find the solution to the job problem? So can this is the this particular thing we already seen, capacity of single neuron, that it cannot solve the job problem, linearly inseparable problem. And but unless the input transform to the bit representation in this, but you will see that using this particular equation, we can what we actually going to find. That is very interesting. Yes. Now here also you can say that how MLP can be realized by a group of SLP, SLPs. So this is the interesting question. Now you see that this X1, X2 is input, and these are the SLP kind of thing, because and we put a hidden layer in between. So what does this mean? Now you see a single SLP can be possible to distinguish in this. So the surface of decision surface of a single SLP is look like this. Okay. And another problem, this another single SLP can be this kind of, or this is another kind of. Okay. Now the idea is that, just for example, what I'm trying to say, that now if there is a okay, so this is the kind of Zod problem. Now the question is that a single decision boundary cannot distinguish between these 2 points. But if you check it here, so if this two decision boundary if you take, then this problem can be solved, because this is clearly a decision boundary. So here exactly this is the one hidden layer, this is another hidden layer, this is another hidden layer. If you adjoin these three, what will be the set? You see here, this, and we can get these two. So if we add all these four, this, and this, we can get this kind of. But within a single hidden layer, you cannot get it. So 4 hidden layer, you are in a particular 4 hidden layer, you can add. Okay, the same thing you can see here. 1, 2, 3, 4. If these 4 hidden layers is the first layer, that hidden layer is adjoined here to get this. So this thing is basically, this represent this represent, sorry, this represent this represent this, and this represent this. But you adjoin these 4 and get this complicated pattern. Okay. So that is very way to handle this complicated. What is actually true is that if you use this kind of, so you what you have done, you just put a hidden layer here. Now if you are get a more hidden layer, you can get by this. If you say that, okay, you can get this, and then in next layer we can get this. So in the next layer we can get this. And if I go in this way, we can get, even we can get a very complicated thing. Maybe we can get a circle. Okay. And if we go beyond another thing, we can get a kind of square. So that is the way we are trying to do. So that means that the multiple hidden layer makes sense. To represent, you can say to represent a complex pattern. Okay, this is the idea. Exactly. If you send the problem in this, in a decision-based boundary thing, that this kind of thing will give you such kind of decision boundary. So, universal approximation theorem: a single hidden neural network with a linear output can approximate any continuous function arbitrarily well given enough hidden units. The result applies for sigma, tangent, and many other sigma activation. This is good result, but it doesn't mean there is a learning algorithm that can find the necessary parameter values. That is the problem. Until 2006, the major problem of this, that there is no good training algorithm for multiple hidden layers movement. And that from 2006, the things has been started changing drastically. There is no, there is no multiple. That was the major problem. Okay. So adjust neural network weights to map inputs to outputs. Use a set of sample patterns where the desired output inputs percentage is known. The purpose is to learn the generalized recognized feature which are common to the wooden diagram. So here, just we in today's class, because backpropagation is basically a big thing. So I think we stop here today. And so we'll start backpropagation from the post midterm class. If you have any question, you can ask. Otherwise, up to this, the syllabus for the mid-semester examination. So if you have any question, you please ask. Because today is the last class. Thank you.